All right, sound check. Good to go. All right. So yeah, as mentioned, I'm Tom Talpey. I'm with Microsoft. I've been to a bunch of these, presented last year. You'll see some of the slides from last year again. I'm going to take a different tack from Andy's, and it's actually going to dive in on three basic areas. I'm going to start off with the SNIA NVM programming model and the way we're extending it to support remote programming. Second, the new RDMA semantics that Andy mentioned. This is a bit of a review. I hope most people are aware that this is going on. But there's some basic functionality and some extended functionality that I definitely want to talk about. And finally, Windows persistent memory support. With Microsoft, and here I am, so I got to throw this in. It's much more mature than you might think when you listen to Andy's talk, which is largely speculative. It's quite real in both Linux and Windows today. And I'll just talk a little bit about Windows. This is more local than remote at this time in the Windows support, but I'll give you the details. Okay, so I got a lot of stuff and a half an hour, so here we go. This is a bit of a review. The persistent memory model that SNIA uses is organized into two basic areas, a volume mode and a file mode. Volume mode is sort of the whole device, right? It's the volume on which the persistent memory resides. And the file mode is more of an application view of a file which resides on persistent memory. And the two are used in various important ways to distinguish between the types. Volume mode is usually provided by a kernel, right, where you have a whole device. And file mode is usually provided by a kernel with a user library. Sometimes it's completely in user space. In fact, that's ideal. But you can see these two little squiggly red lines. You can't give a SNIA NVMP presentation without saying the word squiggly red line. Those are the interfaces. Map and sync. As Andy mentioned, the mapping of a file is the most natural way to access memory as storage. And it associates memory addresses with an open file, right? This is a traditional API. Callers may request an address. Sync is a little more subtle, however. MSync or flush view of file on Windows do cache buffer flushes, right, within file systems. Here, we're actually flushing the CPU cache. This is actually a hardware flush. And so there's more to it than simple MSync. And the two types that we've identified in SNIA are called optimized flush, which is the current version that we've published, and a second new one called async flush, and that's where I'm going to spend a little time. Async flush is sort of like a deconstructed optimized flush. It's the flush followed by a drain. The flush is executed asynchronously. It's really important. But just a quick warning, and I'm going to go into a little more detail here. Sync does not guarantee order. The ordering is relaxed ordering, and it's very, very important to realize that. So where the SNIA NVM programming twig is going, we've already established if you will, the local interface with local applications, local persistent memory arrays, and a local API to allow the application to manage it. Where we're going in the next revision, the next cycle of development within the twig, is to extend this to remote. And once again, you can see a squiggly line. It's kind of a solid line here. But basically, it's an adapter on top of the existing PM-aware file system that we had in the previous picture. But we're going to add over here at the right a network adapter that allows replication or other communication to peer B. And we're analyzing the types of workloads and the types of applications that are going to benefit from this. The most important new semantic of the NVMP interface, we should stop short of calling it an API. That's what we hope the OpenFabrics Alliance affiliation will give us, right? It will instantiate this as a real API. But we call it an interface in that SNIA is defining the abstract requirements of the interface. And the async flush is probably the most important one for remote. As I mentioned, it's an optimized flush which does not wait for draining, right? Optimized flush was intended to be a user space, highly optimized, highly efficient way of flushing to persistent memory. And it was a synchronous call. Basically, you'd call flush, and it would flush, and it would return when the flush was complete. Async flush, we've taken this apart. You can think of it, if you're familiar with the x86 instruction set, Andy mentioned these two in passing. CL flush, and it's a variant called CL flush opt, is cache line flush. It allows you to flush a single cache line. And so by invoking CL flush carefully, you can flush it out of the CPU cache and into memory. I'll show you a picture. But it requires a subsequent drain call, and that's what we call sfence in x86, storage fence. It stops the execution until that flush is complete, right? Basically, CL flush asks for it to be flushed, but then, the cache and the hardware all has to do its thing. So sfence waits for it. So you don't know that the flush is safe until the drain has returned. We anticipate this use by parallel programming, right? You can move data to the device and you can continue to do more work while that data is moving, right? But in particular, remote programming, where we've got a NIC that needs to move data. And that's really important. So that's where we go. And so here's a picture of the async flush semantic. These are kind of pale. I hope you can see this presentation online where you can get a little more detail. But it's important to note that the async flush defines the ordering of durability, and only the ordering of durability. It doesn't define a memory order. It doesn't define what order the cache actually pushes things, for instance, to memory. We disassemble the idea into consistency or visibility and persistency or durability. And that word visibility, by the way, I just have to say one thing that Andy mentioned. He said, the higher up in the stack we surface the persistent memory, the more leverage we get from persistent memory. Does this sound familiar to RDMA programmers? If you hide RDMA under some layer, do you get the same advantage that if you expose RDMA all the way up? I've done RDMA for a lot longer than I've done persistent memory, and the parallels are so distinct. They're so similar, these approaches. Anyway, that's purely in passing. So, down here where you see these load stores, right? Here's a memory API. We have 4 instructions, sort of. We have a load, a read, a store, a write, a flush, and a drain, all right? That's our memory API. The store goes into this little animal called a store buffer that's just there to make your life difficult. But it's consistent with the cache, so it's visible. Everything up here is visible. But only down here does it actually go into anything, and only on the right does it become persistent. And these loads and stores happen completely asynchronously from these loads and stores. Well, that's very much like RDMA, but it's relaxed ordering down here. And the load stores put data in visibility, but only the flushes move it to durability, right? So you can think of it like a 2-step process. A local implementation, load is load, store is store. That's simple, right? These are move instructions on x86. Async flush, once again, is a CL flush. And drain is a PMEM drain on x86 that'll turn into an sfence. Well, what happens if we want to make this remote? It's actually quite simple and quite straightforward, but you have to look at the bottom of the picture instead of the top of the picture. Load is still load and store is still store. Those put the data in visibility space. But durability, to move it across the network to your peer, is basically an RDMA write. It's as if the cache were writing to memory, but we're going to take it from local CPU space to remote CPU space with an RDMA write. So basically, we defer the writes until the application calls flush. You might say, why don't we just do it at load and store time? There are 2 big problems. The first is efficiency, taking a trap, and second is precision. You can only take a fault on a whole page. You might only want to move a very small amount of data. Drain, whoopsie, wrong button. Whoa. Drain, in turn, turns into an RDMA flush. And that RDMA flush is what I'm going to talk about next. Okay, new RDMA semantics. The RDMA protocols are challenged with PMEM because we need a remote guarantee of durability, not visibility, which is what RDMA normally provides, right? You do an RDMA write to the other side, it's guaranteed to be visible to the other side at some point, but it's not really guaranteed to be in any particular place in the hardware, right? It's just that if the CPU or some other bus device reads it, it'll see the data you wrote. And so you can think of it a little bit like the CPU cache to memory semantic that we just had down below. It's visible, but it's not yet durable. And so it also doesn't guarantee ordered delivery, RDMA write. Very different, right? So we require an extension, and we called it RDMA flush. This has been discussed in the IBTA for about a year, and its proposal is to execute it as a non-posted operation, just like an RDMA read or RDMA atomic, but it performs a flush from the device on the remote peer. It's ordered, it's flow controlled, and it's acknowledged, just like an RDMA read or an RDMA atomic. Ordering is probably the most important function here. The initiator requests a specific byte range to be made durable, and the responder has to guarantee that at least that byte range was made durable. It can make everything durable, it can make a little bit more durable, whatever it chooses, but at least that byte range must be made durable. And it acknowledges only when the durability is complete. And this is moving along really, really well in the IBTA. The NIC vendors and some of the application requirements all seem to be met by this new operation called RDMA flush. It's going well. It's a new wire operation, as I mentioned, and it's also a new verb. So there will be visibility up into the lower layers of the programming. It's implementable in both IWARP and Rocky, InfiniBand and Rocky. There's an IWARP draft that I wrote a couple of years ago that needs to be refreshed now that we've moved on in the IB Rocky area. This is mostly I said, but basically the receiving RNIC queues the operation and proceeds in order. That's really, really important. The push pending writes to targeted regions, that's a platform-specific thing. There's currently no flush on the PCI bus message protocol. So there may be some issues with implementing this on some platforms. There have been a lot of discussions about this at storage developer conferences. Chet Douglas of Intel has talked about so-called workarounds to enable this to take place. Worst case, it just interrupts the CPU and says, I can't figure out how to do the flush, you have to do it for me. But that's undesirable because of the latency. The idea of this is to keep the latency very, very low. But these are implementation questions, not protocol questions. The protocol and the interface are the hard things. The implementation will be definitely different on different platforms. So that's good. We're doing the hard stuff first, right? The RNIC responds only when durability is assured, okay? So that's the basic semantic. We request it to be flush, it's been made durable. We didn't provide any data when this happened. The data was all provided earlier with those RDMA writes that I referred to. But it's flushed, it becomes durable. That's the only guarantee that this operation makes. So there's broad IBTA agreement on this. It's moving along quite well. There are some semantic details. One of the most important ones is what's the argument to the flush verb? Is it a segment? Is it a memory region, everything with the same handle? Or is it the whole queue pair? Right now, it's the whole queue pair. And the important reason for that is ordering. You don't want to scoreboard all the writes that landed on a particular region. NICs don't do that today. And you definitely don't scoreboard each byte that went across the wire. So it's easier just to say, every sequence number that might have been a write that happened before, make sure that's been pushed before I flush. And so that's a nice, simple thing. But it's an open question whether per segment or per region are implementable with some efficiency. And so that's still sort of on the table. And it's possible that the verb, probable that the verb will specify a segment or a scatter-gather list of segments, even though it may not have that semantic. There are implications on the API, of course, and it's important that the SNIA twig, that the verb, that the OpenFabrics Alliance, that all these sort of interface-focused organizations all agree on the semantic. That's what we're trying to drive. There's a second operation called a non-posted write for a write after flush. I'll give a little detail. I'll just try to spin through some extra credit operations. There are actually about 4 other semantics that I want. Non-posted write is the one that's currently on the table. It's useful for log writes and transactions. It's an atomic place after write, or place after flush semantic. Really, really useful. And as I mentioned, we may need some PCI Express extensions. So here's a ladder diagram. And there are 2 entry points, so actually 3 over on the left. And they're alternatives. Optimized flush, which enters at the top, basically flows all the way down. Oh, oops, that's the off button, isn't it? And it basically goes right, 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 flush, right? And then the flush goes through and it comes back and acknowledges. In the alternate implementation, it's 2 calls. It's an async flush, which does right, 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 and a drain, which performs the flush at the end. Semantically, they're the same, but there is less of a bubble in between there. You can do multiple flushes and a single drain, for instance, or you can do other work while that's happening. So this is roughly the ladder diagram. But you can see here that the RDMA writes are sent on the wire and become local writes to memory, where that little lasso tries to grab them all. And that lasso makes sure that those local memory writes are complete before it allows the flush to complete. So here's an example of an upper layer workflow for a log writer. And I won't spend too much time on this, but in a log writer, you write a log record, maybe a K, 4K, some medium-sized hunk of data. You make sure that it's durable. You make sure that it is recoverable after failure. And then you write a pointer that brings that log record into the linked list of currently committed transactions, right? So it's important that you not write the pointer until the record is safe, right? It would be really, really bad if the pointer landed on the disk before the record. So there is a, I must have clicked something. So there's a break. And second, there's a critical latency point right there at that comma that you can't start writing that log pointer until the log record is safe. And if all we did was write flush, we'd have to do write, 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 flush, write, flush. And we'd have to wait for that first flush before we could issue the second write. That would be a pipeline bubble. That would be latency. That would be bad. So by saying we have a write after flush operation, this so-called non-posted write, we take that bubble right out. And it's once again a non-posted operation, so it executes like a read on a queue after the flush. And this fits in rather nicely. This is being actively discussed in IBTA, and pretty sure it'll move forward. But there are a few other things. All right, so in the interest of time, I'm just going to spin through these. But here's an example of writes and write after flush. Sorry, I forgot to add this. So we do put, then we do a flush. And then we have a second write after flush, which waits, see that stop sign, for the first flush before it completes. And the write is actually not acknowledged in this case. Only the flush is acknowledged. RDMA write isn't really acknowledged, right? There's a transport ACK, but there's no real upper layer ACK for RDMA write. So this is highly efficient. There's no transport bubble. There are a few other things that I personally want and I've been arguing for, but I'm just going to mention them real quick. One is verify. How do we know that the data that we wrote and flushed is good? Normally we'll have a storage protocol, right, that will check the integrity of the data. We have a file system that will check the integrity of the data. And if something goes wrong, these things will raise errors, right? And they'll say packet corrupted or disk sector corrupted or whatever. It will perhaps drop multiple copies, things like that. At this level, though, we don't even have a CPU that's aware of it. All we have is a pair of NICs. And so I argue that it's really, really important to get to the final goal of this, to have a verify operation. And I've defined some of the verify semantics here, but it basically hashes the result. And if the hashes don't match, that's a failed verify. Here's a little picture of it. Write flush and verify. So here's where we do a flush, and we finally follow it up with a verify. And the verify would complete the transaction. Some of this could actually overlap if we merge the verify and the flush. That's my wacky idea. Nick vendors may or may not like that idea. That'll take another bubble out of the pipeline. Privacy. RDMA has never really had any sort of privacy story, right? And privacy is interesting because this is user data. We don't want to protect it with a machine key, right? Maybe we're sharing this machine. Maybe there's a bunch of VMs on this machine. So it's really important. The granularity and the keying is really the problem. And there are some other issues. On disk crypto, some people would say, let's just use the data at rest. And there's some real problems with that. But a typical approach for most network protocols is to use a stream cipher and to use an authenticated cipher, which provides integrity as well as privacy. So here's another wacky idea in which a nonce for the authenticated cipher is stored in the memory region. And the memory region is used by the NIC to encrypt and decrypt data in flight. And this would actually work rather well. I've had some interesting discussions about it, but it's not yet on a piece of paper in a standards group. Cipher housekeeping is a really interesting problem. And in the interest of time, I'm not going to go into it too much. RDMA QoS. The last problem we have is we have memory, right? Which is a very low latency and high bandwidth device. Well, we have networks that are low latency and high bandwidth, and guess what? You plug one into the other, and there ain't no stopping either one of them, right? You don't have a sort of a natural choke point in your pipeline. So these devices and modern CPUs can easily saturate 100 gigabit and up networks, easily. And so you got one data stream using 100% of your network. That's a bad day. Well, at least it's a bad day in a thing that wasn't designed, that was designed to share. And so there really needs to be some sort of QoS at the RDMA layer to enable this. And that QoS needs to be fairly fine-grained and sort of an end-to-end QoS. Not just how much of what percentage of the bandwidth am I using. There's a policy and there's a lot of stuff in here. There's been a ton of work in file systems and network file systems about this. I propose they be added here. But worst case, they could just be done on upper layers that use persistent memory. But I'd love to see them also addressed at the RDMA layer. OK, the last segment of my talk is just to talk about something real, Windows persistent memory support, and just give you a little bit of insight into where Windows is at in this. It's very similar to where Linux is at, but there are some very distinct differences between them at the details. I'm just going to talk about Windows. I'm not going to talk about Linux here. Persistent memory is fully supported by Windows. It has been since late 2016. We shipped PMEM support to basically recognize a JEDEC NVDIMM-N device. We shipped that in the fall of 2016 when we shipped Windows 10 Anniversary Update and also Windows Server 2016. So if you take either one of those machines, you run them on the appropriate piece of hardware, and you drop an NVDIMM-N into it, it will recognize it, enumerate it, and implement a bus driver which basically exposes it. You can create various services on top of it. I'll tell you what those are in just a second. But it's real. And recently, I just want to mention, since Andy mentioned it, PMDK, the Persistent Memory Developer Kit, is fully supported by Windows. And there's source and binary available on GitHub. So you can bring these things into an existing Windows machine, in binary form, run them there, and experiment with them. So that's pretty cool. So here's a little picture of Windows PMEM access. There are basically three modes that I'll talk about. At the top left, DAX mode, referring to the data path that's over here on the right. this direct access application through the DAX file system down to a PMEM device. And this thick green line, which is the hot path for data access, where that application can get straight to memory. So load store, that's a load store instruction path. All right, fully supported in Windows. It's our version of nvm.pm.file. Okay, it's the native Windows API, but with a mapped file and a little bit of care, that's what it is. I'll actually show you a code example in just a minute. Second mode is block mode. That's the one on the left. That's where we have a block mode application that does not go through the file system, but goes straight to the disk driver, right? And so it actually bypasses the file system straight to the disk driver, which is basically a RAM disk on PMEM. And there's a little bit of awareness that it's PMEM, that it requires flushes, okay? But it's basically a block I/O model. That's our version of nvm.pm.volume. And once again, it's standard legacy stuff. Right? This is an application that opened a volume and reads and writes it on a block basis. Okay? Once again, supported on persistent memory devices. And finally, a whole class of PMEM-aware applications. These are PMDK applications, open-coded applications, and things written to a native Windows API called RTL, the runtime library. Here they are, the Windows native PMEM APIs. Now these appeared in spring of 2017, about a year ago in Windows 10. We haven't shipped Windows Server since 2016, but the next version of Windows Server will have these same APIs. They're basically 6 or 7 APIs. Get non-volatile token is a sort of a state acquisition where you're going to describe the region in a token, which is just a local variable in the library. Write, flush, and drain are the APIs that I just told you about. And finally, free non-volatile token to clean up. These are all fully documented, fully supported, and they work in both user and kernel modes. So kernel applications will use this same runtime library, by the way. DAX in Windows, here's how to create it. This is kind of boring. But flush code. So this is traditional code in Windows. The first version is how to map a file, how to get a base address for the mapping, and how to write it, and then flush view a file. This would work for ordinary file mapped files in Windows today. But it works when you open it on a DAX file to PMEM. You can also open code it. Instead of calling memcopy and flush view file, you can do a non-temporal move. That's another RTL instruction which calls the non-temporal versions of the x86 and other processor instruction sets. So that's the open-coded version, implicit flush, right? It looks like you're flushing a file. You're actually flushing memory. It's also possible to explicitly open memory, a memory file, and explicitly flush it using that RTL. And so you can see here in that green line, RTL flush non-volatile memory with a flags of 0 performs a flush of that actual memory region. Only 4 bytes, but it probably flushed more. And then there's asynchronous flush, in which you take apart that flush into a async flush followed by a drain. And here I marked the async flush in red because by simply adding that flag to the flush non-volatile memory API, we wind up with an asynchronous version of it. And then when we're ready, we call drain. And my last little example for Windows before I'm done is going remote, SMB3. I've talked about this at SDC. I think I talked about this last year here. But I just want to mention there are 3 ways to access remote files when this thing comes along. One is traditional I/O, the way SMB works today. One is a DAX mapped I/O, which uses memory copy on the server side. And one is a DAX mapped remote I/O that uses these APIs plus an extended RDMA adapter to perform this. And the latency of this is expected to be in the single digits microseconds. We'll tell you when we can show you one. Some links. And one more public service note. Andy and I have talked about SNIA and the SNIA non-volatile memory programming twig. There's a table, an information table out in the lobby for SNIA. It has some information about the twigs and the SNIA process, information about the Storage Developer Conference. And if you're interested in contributing to the twig, which would be really great, there's a table out there with more info. Thanks. I'm kind of right on time, so I don't know if there's time for a question, but of course, I'm happy to.
Maybe one question.
Hi, Tom.
Hi, Prof.
So one question. We are in 2018. If I fast forward to 2020 or 21
Yep.
with Ohio State University's presentation of the performance numbers difference between implementing this in software where the remote host opens the file and does the write without any new IBT extensions which we are working on. With the accelerated verify and flush RDMA operations versus software doing that in the remote host, what's the anticipation in latency?
Probably this is the best example of that. An existing SMB protocol which allows the client to send a request to a server who performs the local operation to the DIM. SMB, when you send a message, interrupt a process, queue a work request, perform the work, and reply, tends to take 30 to 50 microseconds, right? Regardless of what I/O you perform. By doing push, you avoid all the overhead on that server process. It doesn't even take an interrupt. Only the NIC in the purple box performs the operation. Right. We've been able to measure that in the sub-10 single-digit microsecond range. So if you take 30 is actually really best case. 50 is more typical. And the tail latencies tend to be fairly high. Sometimes you'll see 100. The tail latencies of this push mode are extremely low. They're very tight latencies. So you're seeing basically an order of magnitude.
Great. So the next follow-on is, so is SMB aware? Usually a storage is a tiered storage, where we have mix of memories or mix of storage with SSD, hard disks.
Yeah, but block devices, right.
So is SMB aware, or it's already inbuilt into the protocol where the host knows that out of 1 terabyte of file system exposed, this 500 gigabytes is persistent memory, and therefore I need to do RDMA verify.
Yeah, so that comes from the file system. You can query the attributes of the file, and it will tell you those types of things. And SMB is, of course, a file protocol. So by querying the DAX file system, you can query the type of device. And SMB supports storage normally. So there's really, to implement the full push mode, only 2 operations need to be added to SMB, and one of them is optional. Basically, it's register this as a memory segment and give me a handle so I can do the RDMA. Normally, the server does the RDMA.
Right. Okay, thanks.
Thank you.
Thanks.